In today's lecture, the first thing that we are going to discuss is the correspondence principle. So what is the correspondence principle? Suppose we discover a new law of physics that describes some new regime in which that equation or that law is applicable. So usually we can take a limit of that regime to get to a regime where some older physics laws are applicable. So it is always the burden of some new theory of physics that in that limit where we regain the old regime, that this old physical phenomena must be explainable by the new equation. So the correspondence principle has roots in that. Quantum mechanics claims to underpin the classical world. And therefore, in situations in which, say, the masses or the dimensions of the quantum systems approach those of classical physics, so that is the macroscopic masses and dimensions that we are used to, then the correspondence principle says that quantum mechanics must reproduce the expectations that we have from classical physics. In fact, we use the correspondence principle already without mentioning it. So for example, when we were deriving the operator for the momentum operator, we used the idea that the average value of momentum of a system should be given by mass times the time derivative of the average value of the position of that system. So this is a classical equation, and the correspondence principle was invoked in using this equation to figure out from the expectation value of x what the operator should be for the momentum. So in the future, we shall point out other instances of this principle. Now, although the correspondence principle tells us or gives us a guideline as to how we can regain the classical world from the quantum world, this is not as straightforward as taking a limit. Often, there are things which happen in quantum world where in no limit can we have a phenomena which is also present in the classical world. For example, take the case where we have a free particle. So a particle, can go to the left or it can go to the right. And in quantum mechanics, these two states are represented by two different wave functions. But because the Schrödinger equation is a linear equation, we saw that if we take a linear combination of these two wave functions, then the resulting linear combination is also a solution to Schrödinger equation. So psi is also a solution, a physically valid state. But if we want to observe the momentum of the particle, we find it either going left or going right. We never find it in a superposition of left and right. So even though the superposition of two physically valid state is also a physically valid state, this can easily lead to a kind of paradox in the classical world. So to illustrate this paradox, Schrödinger introduced the idea of the Schrödinger's cat, where he rigged up a system where a quantum system which has two quantum mechanically valid state like psi1 and psi2 somehow got entangled with the state of a cat which is alive and the state of a cat which is dead. And he used this to kind of show that how the idea of superposition at the quantum world, if this were to somehow spill over to the idea of superposition in the classical world, would lead to some kind of paradox. Anyway, I don't want to discuss the Schrödinger cat paradox in detail, but I just wanted to point out that the correspondence principle is not as straightforward as it would appear to be at first glimpse.